Ladies and gentlemen, last but not least, it's my great pleasure to have Paweł Pilarczyk, and Paweł will tell us about topological methods for computational analysis and dynamics.
Thank you for coming. I'm going to talk about a few different computational methods for mathematics that I've been using in my research for several years. And this will be sort of a mixture of algebraic topology, numerical analysis, and graph algorithms. But I'm trying to explain this in such a way that you have some understanding, not just you feel that there is a lot of mathematics behind, but that you can grasp some ideas of what this is all about. The title is precisely the same as the title of my talk at the conference, and this is not a mistake. In fact, some of the first slides will be identical, because in the conference I'm going to talk about some general results in this area, while here I wanted to give you some hands-on experience so that you can feel how how working on this computational mathematics in this area, what it looks like, and how one feels working on this. So the plan for the talk, for this mini course is the following. First, I'm going to introduce some terminology on dynamical systems and the Conley Index. By the way, how many of you are familiar with the Conley Index? Okay, quite a few people, and for the others, I assume that you are at least a little bit familiar with the notion of dynamical systems. I'm going to recall the definition in a minute. Then I'm going to talk about a computational method for classification of global dynamics. The general idea is that we have a dynamical system. There are several parameters. For example, this could be a population model or some model of a chemical reaction, and we don't know the values, the specific values of parameters, and we would like to scan all these ranges of parameters and see what the dynamics is like, if the solution stabilize, or if there are some oscillations, or maybe something else. So this is a general plan, and using the topological methods actually makes this plan possible, at least to a certain extent. And in the third part, I'll show you some software libraries and some specific software that is written mainly in C++, so that you can use the computer lab and everybody can download, compile, and run some actual computations. The actual computations I do for my research take several hours of a computer cluster. So for this workshop, I selected just a tiny piece of the computation that can be done within a couple of minutes on a PC. And hopefully everything will work. The computer guys are here until 5 only. So if not, then after 5, we are on our own. Okay, so let's begin with the first part. This is the formal definition of a dynamical system. The general idea is that there is some rule for how points in the space move in forward time. Let me skip this part. For example, if we have a map, then this map defines the dynamics on X, which we call the phase space or space, in such a way that we look at iterates of points. We have a map, continuous map. It could be invertible, but not necessarily. In some practical applications, the map is not invertible. And there's a rule. If we have a point here, then it moves to the next position, another, and so on. And we look at what kind of trajectories we can observe in this system. If we have an ODE, an ordinary differential equation, on some space like Rn, then this defines a flow. Solutions in forward time define trajectories. This could be some mechanical systems like the trajectory of a bullet that is shot from a cannon, contemporary applications, or some other dynamical systems. And the formal definition says that after time 0, you don't move. And if you move a point after time t and then after time s, then it's the same as if it was moved by the time t plus s at one fell swoop. This is a picture of some typical dynamical system of a few trajectories in a dynamical system with continuous time. The time is measured by real numbers. And now I'm going to introduce some notions that are going to be used for the analysis of dynamics. So we say that some set is invariant if it does not change under the dynamics. For example, if there is a fixed point, that's if a trajectory starts from that point, then the map, after the map, it points to itself, so it doesn't move. This is a stationary point, and this is just a one-point invariant set. If there is some disk of trajectories that go around some point, this is also an invariant set. A single trajectory is an invariant set because it does not change. It moves with the time, but as a set itself, it does not change in time. And we would like to split the dynamics into invariant sets, but we don't want the sets to touch each other. So we want to have them isolated. So first, given any set in this phase space, we say that its invariant part is the largest invariant set that still stays inside this set N. For example, here I put gray, 4 sets marked in gray. And if we look at this round set here, every trajectory leaves this set in forward or in backward time, except for this point. So the invariant part of this disk will be just this single point. Here we have a larger invariant part. Here we also have one point, and here we have an entire looping trajectory, periodic order. We say that this gray set is an isolated neighborhood if it is compact and its invariant part is contained in its interior. Normally in topology, neighborhoods are open sets, but a general definition of an open set of a neighborhood is that it is any set such that it contains this part that its neighborhood for in its interior. And this is the notion that is traditionally used in this part of maths. And we say that some set is an isolated invariant set if it is not just an invariant set, but it is isolated by having some isolating neighborhood. For example, this fixed point is isolated because in its neighborhood, it is the only invariant set. If you look at this point in the middle, it is an invariant set, but it is not isolated because no matter how small neighborhood you take, there will be some additional periodic orbits that fit into this neighborhood. So if you want to take, for example, this entire large disk, then this will be an isolated invariant set because some other trajectories actually gain some distance and leave this neighborhood in forward time. By the way, if there is anything unclear or you need some more explanations, please stop me. We have plenty of time. It's important that you understand the ideas. Now let's look at some simple class of flows, the gradient flow. So suppose we have some surface in the space. And everything moves downwards on this surface. And in general, in generic position, the dynamics, this kind of gradient dynamics is very simple. There are some critical points, which are fixed points in this dynamics. There are some trajectories that go in forward time to some critical point, in backward time also they go to some critical point. So the description of this dynamics is very simple. You can describe it by means of a directed graph. A directed graph is a mathematical structure of in computer science where you have several nodes and you have some arcs or edges. Here we have directed edges, which are called arcs sometimes, but I would also call them edges in the graph. And these edges indicate possible trajectories joining this node with this node. Each node corresponds to a critical point. I've numbered them starting from 0. Like in mathematics, everything starts from 1. In computer science, we number from 0. And I am a mathematician, but on the other hand, my qualifications are also in computer science. So with this application, I number from 0. So here we have the numbers 0, 1, 2, 3, 4, and 5. And the dimension of the unstable manifold, this is like the dimension of where trajectories leave this neighborhood, is called the Morse Index. If we have a repeller, then this entire surface around this repeller leaves its vicinity. So the dimension of the unstable manifold is 2. For a saddle, there is one direction where trajectories get close to the saddle. There's one direction where they leave the saddle, and all the other trajectories just pass by. So the Morse index is 1. I put it here. And for an attractor, there's no unstable direction. Everything flows to the attractor. So the Morse index is 0. So this notion of dimension of the unstable manifold works fine for gradient flows. And in fact, we would like to catch the global dynamics by means of a gradient flow, so that we have this kind of a graph where we have some critical points, and then we have trajectories that can join these points. Here you need to look for paths, possible paths in the graph. For example, there is a trajectory from this repeller to this attractor from 1 to 5, and this corresponds to this path in the graph. I don't draw all the possible directed edges. We just use the transitive reduction of the graph. Otherwise, the graph will have a lot of edges. It will be difficult to read out the information from the graph. Okay, so to do this in this general setting where we don't just have critical points, we also have some more complicated isolated invariant sets. Conley in the 70s introduced the notion of a Morse decomposition, and then he also introduced the notion of the Conley index, which I'm going to explain in quite a bit of detail here today. So we look at all the isolated invariant sets, and we would like to put them in such an order that the flow mimics this gradient situation. In the gradient flow, it is not possible to go back to a higher level because all the dynamics flows downwards. We would like to have the same situation here. So this is a formal definition, but I'm not going to read it. I'm just going to explain what it looks like here. If we collapse each of these isolated invariant sets to a single blob, we look at all possible connecting trajectories, then there should be no loop in such a trajectory. In other words, there should be a partial order on the isolated invariant sets, on these Morse sets. We can push some of the sets higher, some lower, so that we have the graph that mimics the gradient flow. And the general idea for the classification of global dynamics on the phase space is to look for all the recurrent dynamics, to treat these recurrent sets as single units of dynamics, and then to look for possible connecting trajectories between them, so that we have this kind of a brief description of the dynamical system. Okay, so this was about the gradient-like structure. Now, we would like to get some information about the individual the individual isolated invariant sets. Like these critical points, the Morse index characterizes the types of dynamics around such a critical point. Here we have more sophisticated sets, so also the notion of dynamics around such a set will be more tricky. And this is done by means of the Conley index. Notion of the Conley index is defined on the basis of an index pair. So for each isolated invariant sets, we try and construct an index pair in such a way that we take that this blue is an isolating neighborhood, and we look at the part of the isolated neighborhood through which the trajectories exit this neighborhood. So here in red, this is what is called the exit set. And the formal definition says that if we have a trajectory that after some time is in the exit set, that it cannot go back, it must leave. It's like in a supermarket. Once you're in this shopping area, you must leave through cashier's line. Otherwise, they will not allow you to leave the supermarket. So if you get there, you must leave. You can enter the supermarket later on, but once you are behind the cashier's line, you cannot go directly back to the supermarket area. The next condition is, these are the conditions I've just told about. And the third, so we have this isolated neighborhood, and trajectories leave through the exit set, and from the exit set, there's no direct way back to this neighborhood. So these are the three conditions. And now the Conley index is the relative homology of this index pair. I assume that we all know the notion of homology. Is there anybody who doesn't know what homology is? Regarding the Conley index, it is a very useful topological invariant because every isolated invariant set has an index pair. And if we take two different index pairs, that by taking this relative homology, we get the same algebraic object, or it is an isomorphic one. And if the Conley index is non-trivial, this means it is not the zero homology, the zero root, then the isolated invariant set must be non-empty. In order to compute the Conley index, you don't need to know precisely the flow, the dynamical system. You can know this with certain accuracy only, with some limited accuracy. You also don't need to know the actual location of this isolated invariant set, just an isolating neighborhood. So this is something that we can actually construct using rigorous numerics to construct an isolating neighborhood, and then to get the index, the exit set, and then we compute the Conley index. I'll show how this works in practice. First, let's explain the shapes of some popular Conley indices. So there are different kinds of isolated invariant sets that appear often in dynamical systems, like fixed points, periodic orbits. These could be attractors. These could be hyperbolic sets with some unstable direction. There could be also some trivial indices that appear frequently in the computations because there could be some slowdown in the dynamics, so that from the numerical point of view, we cannot prove that the trajectories exit this, say, candidate for an isolating neighborhood. But on the other hand, the invariant part is empty because the flow is just slow. There will be some bifurcation, like a sudden node bifurcation soon, if we change the parameters, but we cannot find this yet. So we must keep in mind that some trivial Conley indices will appear. This is sort of indication that probably the invariant part of such a set is empty. Let me show what the Conley index looks for an attractor, for example. For an attracting fixed point, We can take this isolating neighborhood. The exit set will be empty. So now we compute the quotient space. And now, if you take, say, set P1 divided by the empty set, you don't divide by 0, but this is topology. Okay, so the quotient space is, we say, this is just the set P1, and we add an extra point, we denote it by the asterisk. So when we take the quotient by the empty set, we just add the extra point. So we take this P1 with the extra point. And this is a pointed space, which means that there's this extra point, which doesn't count for homology. So this is relative homology, where this extra point doesn't count. Here, we can squeeze this isolating neighborhood to a single point. We get this asterisk, this extra point. Here we have two connected components, but this asterisk doesn't count as a separate connected component. So the homology is Z in dimension 0, which is the number of connected components. And then there are no other cycles in homology. There are no holes, so there are zeros on all the other levels. Let's take another example. This is also a fixed point, but now it's a saddle-like point. It's hyperbolic. So there's one attractive direction, one repelling direction. An index pair might look like this. We have the P1 is the union of blue and red, and the exit set is red. And if we compute the relative homology, so we can squeeze this set by homotopy, we get the circle with this specific point. This is what all the P2 was collapsed into. And if we look at the relative homology, there's one connected component, but this special point doesn't count for a specific, for a connected component. So we have 0 connected components that are non-trivial. And that's why we get 0 here. And then there's one closed loop at level 1 of homology. So we get 0 and Z. If we have a repelling exit, I didn't revert, I should revert the arrows here. So this should be a repeller. Have a fixed point. All the trajectories are on side. And when we take the isolating neighborhood, this is an example of an isolating neighborhood, and the exit set, the trajectories will be exiting through the boundary of this disk. So these arrows should be reversed in the reverse direction. So here, when we compute the quotient space, this is like collapsing P2. This should also be P2. Sorry for that. P2. Collapsing P2 to a single point, we get the sphere with this extra point. So there's one connected component, but the component that contains this point doesn't count. So we have 0 at level 0 in homology. Then we have 0 at level 1 because there are no non-trivial loops. And there's one void inside this sphere. So we get the Z here at the third position.
I mean, this P2, this P1, this P2 red.
Yeah, this should be P2, and the trajectory should be in the reverse direction. Let's see some more examples. There were also some periodic trajectories. If this is an attracting periodic trajectory, then the exit set is again empty. So we take the P1 and the quotient by the empty set. Division by 0 is forbidden, so we add this extra point. And what we get here is we can squeeze P1 to the circle homotopically, and we get the circle. and this extra point. There are two connected components, but this one doesn't count. So in homology, at level 0, we get the Z. At level 1, we have 1. Oh, here we get Z here. So you see, just by the Conley index, we can distinguish these different cases of oscillating invariances. This is something more sophisticated. If we have a repelling periodic trajectory, then if we take a belt around this trajectory for P1, then the trajectories will be exiting along the whole boundary. Now we take the quotient space, we squeeze, so we have this belt. And now we squeeze its boundary to a single point. What we get here, we can first draw this along this band. So we get sort of a torus, except all this will be squeezed into a single point, which means that we get a torus with no space inside. And this, if we make this space a little longer, suppose my rubber, then we get a sphere with the connection inside. And we can actually move this connection and flip it on the other side of the sphere. So we get the sphere with an extra loop, and they are connected by this special point to which P2 was collapsed. So in homology, we get 0 at level 0 because there's this one connected component and it contains this red dot here, a Z for the circle and another Z for the sphere. So these are some examples, and these are most frequently appearing in isolated invariant sets in typical situations. Now, we can do the same for maps. Suppose this square is squeezed in one direction by the mapping and stretched in another direction. So its image might look like this, in green. And in this way, some points that are close to the boundary will exit. And therefore, for the exit set, we need to take some belt of non-zero width around the boundary of this P1. And this is the image of P2, now indicated in green. The conditions for the index pair are exactly like in the previous case, except now we have a map. We don't have continuous time flow trajectories. Now we have a mapping. So we need to know that the image of the blue part is contained in the union of blue and red, because we cannot exit immediately in one step. We need to go through the exit set. The image of red is the union of red and green, because we cannot go back from the exit set. We need to go outside first, and then we can enter this isolated neighborhood again. And the third condition, very important, this blue part must be an isolating neighborhood. In computation of the Conley index for maps, we also take the quotient for the index space, but we also need to look at the map. How this index pair is mapped to itself with this green part added, because we want to have a map well defined. One can prove that there is the excision property, which means that this green part doesn't touch the blue directly. The green part only can touch the red set, but not entering the blue or touching the blue. Some technical conditions, and this is quite technical to prove that this is well defined and so on. And this mapping is really necessary, because for a map, we can build isolated neighborhoods that have several connected components. The map will build sort of a ladder to map points from one component to another component. So in order to have this property saying that no matter what index pair you construct, it should be the same as long as the isolated invariant set is the same. We need to consider the map and also do some reduction. Like if I take the quotient by the generalized kernel or generalized image, things like that. These are technical things. I'm not going to discuss them here. What is important here, it is the technical difficulty that in addition to computing the relative homology of a pair of sets, we also need to compute the map induced by some continuous map on homology. A typical approach to this problem is to, well, in the textbooks of algebraic topology, is to go through simplicial complexes, some barycentric subdivisions and things like that. It's so painful computationally that we don't do this. Instead, we work with cubicle grids. And there we just use projections. It's much faster. But I'm not going to discuss this in more detail here. Some popular indices are very similar to what we have in the case of flows, except in addition to the space, we also have a map on the space. If this discrete-time system is a tightly map for a flow, then the map will be the identity. Otherwise, this map will correspond to reversing orientation, or if we have, for example, a period 3 orbit, then we have, let's assume it is attracting, then we have an isolating neighborhood that consists of 3 connected components, and then in homology, the homology generators will be mapped. The first generator will be mapped to the second one, the second to the third, and the third to the first. So you can see, you can draw this like a matrix and compute the eigenvalues to confirm this is a matrix of this kind of cyclic method. Okay. So after this lengthy technical introduction to the Conley index, let me now explain the method. So we have, as the input to the method, we have a family of dynamical systems or semi-dynamical systems, because the dynamics needs not be reversible. And we have some parameters. We have n parameters, for example, 3 different parameters or 2 parameters, or in some real systems there are dozens of parameters that we don't know. But the method I'm going to show practically works where we have 2 or 3 different parameters that we vary in some specific ranges. So we need to have bounded ranges for all the parameters. We also restrict our attention to some bounded area in the phase space, like an n-dimensional box. So we have these rectangular regions in the phase space, in the parameter space, and the task is to compute a catalog of all the possible kinds of dynamics in this bounded box in the phase space when we vary the parameters. So we need to do the computations for all the parameters, and we would like to have a rigorous result. This is quite a challenge, but it can be done. Let me explain how. So we switch to cubicle grids. We divide the phase space into a grid of boxes, and then we represent the continuous map. I'm going to explain this for maps, but the same holds for flows. If you have a flow, then we can just take a tiny map for the flow, and it works. There are some theorems saying that this is a good. And we represent this map by means of a graph on the grid. So we take this grid. Each box of the grid is, we compute its image by the map. Suppose it looks like that. We use interval arithmetic for enclosing this image in product of intervals. Do you know what interval arithmetic is? I can say in one sentence. Instead of working with numbers, you work with intervals. And the result of an operation is an outer bound for all the possible results. So if we have, for example, the addition of two intervals, you compute an interval that is wide enough so that the results for the numbers belonging to the domain intervals are all covered by this interval. So this is computing outer estimates for all the operations, for all the arithmetic that is done. So we have, in this way, we compute an outer bound for the real image of the map. And then we cover this by the boxes, by the grid elements. And we cover in such a way that the actual image of the box is contained in the interior of these boxes. By adding this interior here, we get a lot from the mathematical point of view, but the cost is like nothing. It's a lower dense situation that the computed image will be precisely aligned with this grid. In that case, we would have to add an extra layer of boxes if we demand the interior here. But it actually never happens. If we do the computations using rigorous numerics, rounding upwards, downwards, it's nowhere, it's like impossible. Probability zero situation to get this box aligned precisely with the grid. And
do you want to somehow get closer and closer to the isolated invariance by putting this condition?
Yes, so this interior will help with the isolation.
Yeah.
This is a very good point. And in this way, we compute the images of the map. We try to do the computations tight enough, but it is not necessary to really do extremely high precision because we have a finite resolution in terms of the grid anyway. And then we represent this map by means of a directed graph. Here, the vertices of the graph are the grid elements, are these boxes, and the edges in the graph correspond to the mapping. So if this box is mapped to this collection of boxes, then we would put the edges in the graph everywhere. And now it turns out there are some very simple, maybe not simple, but tricky elementary algorithms in graph theory that help us compute a Morse decomposition. If we look at strongly connected path components of the graph, connected component in this kind of a graph is a collection of vertices so that there is a path from each vertex to another vertex and a path that goes backwards from this vertex to this. So we have a path here and another path, for example, here. So these two are in the same strongly connected path component. Typically, people compute strongly connected components without this word path, but we have components with at least one edge so that these components correspond to some dynamics. And this sort of resembles the dynamical system I was showing at the beginning. We have a big disk, it is an invariant set. We have a fixed point, a Cubicle trajectory, and another fixed point. And it turns out that these strongly connected components are isolating neighborhoods. And the dynamics outside of these neighborhoods is gradient-like, and one can prove this because we have computed the map in a rigorous way. And in order to compute these path components, it is very quick. There is an algorithm with linear time complexity, which is the optimal algorithm. The computing time and memory is proportional to the number, to the size of the graph. It's linear.
Sorry? Different functions correspond to different Morse decomposition?
Different functions will correspond to different graphs. Different functions will give rise to different graphs.
sure correspond to different Morse decompositions.
Sure. So and here is this is like this rough representation of this Morse decomposition, and from this Morse decomposition, from these Morse sets, one can also get almost directly. We just take the set, this computed isolating neighborhood, and then we add the forward image for the exit set, and in this way we get an index pair. It just satisfies the two conditions, that the image of the blue part is contained in blue and red, and the image of the red part is disjoint with the blue. For example, those forward images might look like this. So the image of the blue is green, the image of the red is yellow, and they satisfy these two conditions. There is no condition about an isolating neighborhood necessary because we get this for free thanks to taking this interior. Well, I'm cheating a little bit in this picture because this is a multi-valued map. So the green part with the yellow part should overlap. Otherwise, the map is not well defined. For the computation of the cubical homology, relative homology, the cubical map in homology, and the Conley index, we use the Chomp software, computational homology project software. I'm going to show this in the hands-on part in a moment. So now, suppose we have done the computations for, well, we can do the computations for some parameters, where the parameters are fixed. But we want to cover the entire ranges of parameters. So we also subdivide these parameter ranges into grids. And suppose for two different parameter boxes, well, we do the computations for the intervals of parameters. And since we use rigorous numerics, interval arithmetics, the results are valid for each individual parameter. So we get an isolating neighborhood that is good for every parameter in this parameter box. And now we compare the isolating neighborhoods that we got for adjacent parameter boxes. If we can construct a clutching graph that matches the corresponding isolating neighborhoods by means of taking their intersection, and in this way we have one-to-one correspondence between the isolating neighborhoods, we can prove mathematically that there is a sort of continuation of dynamics. So the dynamics is equivalent, and then we subdivide this entire range of parameters into subsets with equivalent dynamics. And we should get a picture like this. Well, this is a result of some real computations. There are large classes of parameters with equivalent dynamics. There are some isolated parameter boxes which have dynamics different from the vicinity. And I'm going to show, actually I can show this right now. So this is 50 by 50 parameter box, which we did for a specific Leslie model. This is a population model, a discrete-time dynamical system with several parameters, but we fixed most of them, and we only vary two parameters. And the dimension could be of this model is arbitrary, so we fixed just dimension 2 so that we can see the dynamics easily. But the software, the theory in general works for any dimension, except for higher dimensions, it is much more costly to do the computations because you have, well, the number of grid elements increases exponentially with the dimension. So let's see. So here are the coordinates of the parameter boxes. Again, I start with 0. In this region, the dynamics looks like this. So there are 3 sets. These little boxes here, black, blue, and red, indicate the order of colors. The black, there's a little, just one single point in the phase space hidden in this corner. The resolution is not so good, so you can't see this. And this corresponds to the first Morse set, which has number 0. It's this one. It has just one box. The homology of the phase space is 0, 0, Z, which means that this is, it looks like a fixed point, but what kind of stability? Yes, it's totally unstable with the two-dimensional unstable manifold. And the map on that sphere in homology maps a generator to minus itself. So this means there is a flip in orientation. It's not just unstable, there is also a flip in the orientation. Now, the set number 1 is built of 1453 boxes. That is the blue one. The homology is 0, Z, 0. So it's like a neighborhood of a saddle fixed point. And the map in homology maps generator 1 to -1. So there is a flip in orientation. Also, and the second, the third with the number 2 has 3,706 boxes. This is this one. The homology of the index pair is Z to the power 2, Z plus B. So there are 2 connected components. The exit set is empty. And the map in homology on the connected components, the first component is mapped to the second one, and the second one is mapped to the first one, which means that we have something like a period to attracting orbit. And this is not a surprise that this is a saddle between this period to orbit, and the orientation is flipped because this set is mapped to this one. So in mapping forward, the orientation gets flipped to the other side. And this is reflected in the Conley indices of these two. Now, when we move with the parameters to this region, these two joined into one single blob. And then when we move forward, we see some other dynamics. Like there is a set that has 3 components, but the Conley index is trivial. This means there is some slowdown in the dynamics, but we couldn't prove that there is any isolated invariant part that could be non-empty. If we move forward, this set splits into 2 components, and they have three connected components each. Let's look at the Conley indices. So the first set, it's again the same, the fixed point at the origin. Now we have the set that has the Conley index 0, Z, three copies of Z, and then 0, and the map maps the first component to the second one, the second to -3rd, and the third to -1st. But this minus indicates that the homology generator was just found in this way and not the other way. It doesn't really indicate the flip in orientation, because after going through this map with the 3 iterations, we get the first generator with the same sign. So this map can be represented by means of a matrix, and we can compute the eigenvalues. Let me explain why the eigenvalues are necessary in a moment. Now let's look at these other 2 indices. Here we get Z3 and then Z and 0. That's interesting. However, the map at level 1 is trivial. That's a disappointment. But this means that there is some loop that is actually filled up in the next iterate. So this is not anything significant from the dynamical point of view. Let me show why. This is also an interesting situation because we have 2 attractors that were found. Now 2 attracting sets, and in the graph they are indicated by yellow boxes. This means that actually it was proved computationally that these are attracting neighborhoods. The image of this entire cubical set that corresponds to this isolated neighborhood is proved to be mapping into its interior. So these are two attractors, and this is set number 2 and number 3. The red one, period 3 attractor, and this big green set inside. And this is an interesting situation from the point of view applications. This is a biological system, and there is like a common belief among biologists saying that the initial state of the population doesn't matter, everything will stabilize eventually. Here we show that there are two possible ways of stabilization of this population. Either everything stabilizes and it's like a fixed point, maybe, or there is a period 3 orbit. If these are two generations like of the population, this means that at some point there are a lot of young individuals in this population. In the next iterate, there are a lot of old individuals, but almost no young individuals. And then there are very few young and old individuals. So this is a little risky to have the population stabilized at this kind of cycle, because some small perturbation might make the population die out. Okay, this is my interpretation. Now, let's see some other example. Here we get 36 generators at level 1, and the map is so sophisticated. That's why, but for the Conley index, you need to compute the generalized image, which means the image of the image of the image and so on. And it turns out that if you compute iterating this image, you get very little, or actually here you get 0. Not 0, but you get just one-dimensional space. And here, that's why the eigenvalues actually reveal how complicated this map is. So we have here the Conley index Z and C. This is the real Conley index. Okay, so this is demo. And now the hands-on experience part. So first, I'm going to introduce the software libraries that are used in this project. The Computational Homology project contains software written in C++ with a lot of optimization for cubicle sets, for this kind of dynamical applications. There is Cubicle Homology and also Simplicial Homology as a byproduct implemented. The Cubicle Homology is where we build spaces of squares, rectangles, cubes, and hypercubes instead of using simplices. This cubical approach is better in some applications because it is natural to have a grid in the form of uniform subdivision in each direction. And also it helps computing maps in homology. And if you have, for example, digital images, then the pixels are naturally boxes or cubes. Even if you have like a 3D MRI scan, then it is also built of boxes.
Does it have any theoretical advantage also?
Theoretical? No. The theory of the homology theory is the same for cubicle setting or any CW complexes. It has just practical advantage. For example, in the n-dimensional space, you can see how many simplices can meet at a single point, arbitrarily many. For cubes, they fill out the space nicely, so there's only a bounded number of cubes that meet at one specific vertex, which helps optimizing data structures, for example.
Some people look also for hyperplanes and cubicle complexes, and it's easy to define hyperplanes.
Okay.
Because you have like, you can divide the square for simplicial complexes.
Yeah. I also know that there this Morse spot homology, different approaches for computing more, the theoretical approaches for Morse spot homology also uses cubicle complexes and never uses simplicial complexes.
Okay.
And that's just theory, but I was wondering what is really the reason.
Well, from the point of view of this research and this project, it is a very practical reason, but everything could be done in terms of simplifying complexes also, except computational maps, for example, in homology would be much more demanding. So this software contains routines for computing relative homology, cubical sets of maps for it contains effective data structures, also graph algorithms like for computing those strongly connected path components. Let me show a web page. So this web page, well, this is free software that is distributed on the GNU General Public License. And there is some description of the software. There's some introduction that explains what homology is, some examples. There are several programs. So this is, first of all, a C++ library that you can use from your own C++ programs. And also there are some command line programs that you can run on data that you generate, for example, from MATLAB. So it's possible, for example, to save a multi-valued cubical map from some MATLAB or some other scripting language, save to a file, then use this program to compute its homology. Okay. There is also a new version at Rutgers University. Okay, I'm no longer in the people section of this software. Okay. Next software, this is a really major software package, the CAPD software developed in Krakow at the Jagiellonian University. The name stands for Computer Assisted Proofs in Dynamics, and they really did several computer assisted proofs in dynamics by rigorous integration of some ODEs. There are even some projects where they dealt with in-dimensional systems by taking a finite representation and then a bound for the remaining part of the system. So they contain a lot of rigorous numerical methods for effective and efficient integration of ODEs. There's also interval arithmetic implemented with all the useful functions like sine, cosine, exponent. There are integration evaluation of maps. They use a representation of sets with varying coordinate systems, which makes it very efficient and effective to compute, for example, Poincare sections, which I didn't use in this program. Let me just show the web page. And so there is the library, and there is also very rich documentation of this library with some tutorials, examples, like getting started sections, like show clever files, linear algebra that is implemented. This is written in C++ using templates. So this is what we call generic programming. And also the RedHom, like reduction homology project, is a subproject of CAPD, which is focused on computing homology of cubical sets, cubical simplicial sets, also persistent homology. And the focus is on geometric reduction of the data sets. So instead of developing very efficient algebraic algorithms, but they're also important, but it turns out that there's a lot more gain if we first reduce those geometric sets, like huge collection of cubes that are all adjacent to each other. We could remove the cubes from the boundary without changing the homology. And this kind of reductions are done very efficiently to make this software work really fast. And eventually the Conley Morse graph software, this is the software that is used for computing these images that I was showing. So there's the computation of a continuation diagram and also a code, a PHP code for the web browser. So once you have computed all these Morse decompositions and the graphs, you can also generate the browser that I was showing a few moments ago. This kind of a set where you can click each box and see the Conley Morse graph and the space form. Okay, so now it's the part to go to the instructions and to try and do some computations here. So first, so in order to use this software, we need to have the C++ compiler, some libraries, and first compile the Chomp software and the CFD library. Some fixes for the CFD library are necessary because I use a version that is slightly outdated, but the new versions change so quickly. I'm not able to update my software that fast with their changes. And the new versions are often not compatible with the previous version. This is what happens when scientists work on development of software. These are not software engineers, these are scientists, mathematicians who develop software. Okay, so this is the address that show the web page address. I can write here www.pewlarczk.com/cm-graphs. This stands for Conley Morse graphs, Conley indices and Morse decompositions. And when you go to this page, CM graphs, there's a general description of this research and some programs. And if you go to the very bottom of the page, there are specific instructions for Linux that were tested in Ubuntu 20.04 for these systems, specifically in this lab for the workshop in Poznań. Here. So the idea is that first it is necessary to install some software on the system. And I asked the software administrator to install the GNU C++ compiler. I think it was already installed here, but there's some other software like Brushbase. LAPAC is the linear algebra package software library. They boost some specific functions. BZ2, this is for compression. So this is already done. Then, in order to browse the results in PHP, it is not enough to have just a web browser. It is necessary also to have a PHP server. And the server is installed here, except we cannot use this publicly. We have to start the server as a private user, and then only it is possible to browse this web page from the computer from which the server was launched. So we don't do these things. The CAPD library. I put here very specific instructions how to compile the library. It takes 10 minutes on this computer. So let's stick to using a precompiled library. I've compiled the library and I compressed the entire directory. It is available for download. So as you know, a computer hacker doesn't really work with the mouse. They open the terminal and they work with the keyboard. So here the idea is that I put all the commands that need to be started in a terminal. So let me open the terminal. Okay, the terminal, and I just copy these commands to the terminal. and do these instructions. So this is wget is getting the file from the web page. This is the zip archive of the library, then making the directory cd4, unzipping this set, and then making a little correction to the path, so that there's the path at which the directory is installed is hard coded into one of the configuration files, and each of us has a different home directory. So this needs to be changed, and there's a program SED that can edit files from command line. This is an instruction for SED to edit the file, replacing home WMI guest 102 with your own home directory. The next step is to download and compile the Chomp library. And let me just copy the instructions here. So the Chomp library can be downloaded from this web page, the download section, and the full Chomp software package. There's the update. It was updated yesterday by myself, and these commands just download this file, create directory, and compile this directory. It takes a couple of seconds. Let me do this now. Now, the CAPD library is compiled in such a way that there are some dynamically loaded libraries, and also it is necessary to enter IDCT to change back to the home directory. And in order for the programs to be able to use those shared libraries, it is necessary to add the path, and also to add the paths for running some programs for the Chomp library. So the next step is modifying the bash RC file by adding the path to executable programs and also the library. And after that, it is necessary to exit the terminal and to start it again. Start the terminal. The next step is to download the Morse graph software and to apply some fixes to the CAPD. So the version I'm using was written some time ago, and the new C++ compilers now complain about the formatting of the C++ code, about some style of programming that is often a cause of mistakes. And that's why I applied these few corrections. Unused result of a function that would read some part of the file, but I'm ignoring this on purpose. So it's okay. Oh. Should I continue, or would you like me to stop for a moment? Okay. So in the meantime, I can show what's topic here. The CPD form subdirectory, which is 52 megabytes. This is the software library. The Chomp library with all the programs, 39 megabytes. The Chomp library, by the way, has some examples how to use the programs. And in the Python section, there is a script that allows browsing with some explanations, like computing the knowledge of the line bubble in the terminal, and you see this Z2 and Z. Those commands created the subdirectory data, which will contain the results of computations, and also the subdirectory zip, which will contain the compressed results of computations, also necessary for the browser of the results.
Tego nie wiem, wiem, że Szomp na tym pracowałem. Teraz na chyba marcu na mojego to przynajmniej stronę, ale nie wiem, czy tylko jest dobra. Więc to cały autor tego to trzeba to sobie napisać po prostu. Na początku Szomp. A to trzeba do niego napisać, zapytać, czy jest taka. No to kompilatory się tak zmieniają, to co kiedyś było dobre, to teraz nie działa. No ładna dziękuję.
Okay, shall we continue? So by now, there is the CPD4 library, the Chomp library, the CMGraph software, and some additional directories created. And this concerns slide setting up the Conley Morse graph software, like compilation of the libraries and of the CMGraph software. And this is the last slide of my presentation. This is the actual using of the CMGraph software. So in this software, there are separate configuration files for defining the map, for defining the phase space, defining the parameter space, and also after the numerical Morse decomposition has been computed, it is possible to add some code that would post-process the Morse sets. For example, we could compute the sizes of the Morse sets, or we could do some further analysis of the dynamics inside the Morse sets. This is our recent project with Justyna and Cubicle Grids at Gdańsk University of Technology, where we not just compute the Conley indices of these Morse sets, but also analyze the internal dynamics of these Morse sets. And the software is set up in such a way that it's possible to run computations on a cluster or on a computer or on a bunch of computers. I developed a software library for communicating of these processes using the TCP/IP. So this is like low-level communication of processors in C++. And in the old days, I was running this software when I didn't have access to any computer cluster. I was running this in a computer lab. I was starting a coordinating process on one computer, and then I was starting multiple computers that would join the computations by connecting at the specific server at some specific port. And then the computations were running. Some computers would suddenly hang up, disconnect from the computations. All this is handled transparently by my module. And now I use this for running this on the computer cluster in such a way that I start the coordinator at some like a access point server, and then I put some tasks in the batch in the queue, like running 100 processes. If I see that the computations are going too slow, then I start another batch of 100 processes, and then they all join the same coordinator, and they together work on the computations. So it's, the philosophy is a little different from the usual running computations on a cluster, where you just enter a prescribed, predefined number of processes. They have a limited amount of time. If they are not done with this within this time, they are all killed, and the computers are gone. And in the next, so after having computed these Morse sets and the Conley Morse graphs, there are some scripts that will produce the PHP code for browsing the results. I wrote all these scripts in Perl. Who actually writes programs in Perl nowadays? Well, I was expecting this. Okay, congratulations. Oh, okay, not necessarily. Perl is a very ugly programming language. At some point, it was an extremely powerful programming language, especially known for its regular expressions. I learned Perl. I wrote a lot of little and larger scripts using Perl. And when I was teaching object-oriented programming to my students, I was showing them C++, Python, Java, and also Perl, PHP, JavaScript. All these languages support object-oriented programming. And this is actually fun to see sometimes completely different syntax for the same data structures. Okay, so let's get back to these instructions. So now the computations are defined in such a way that the directory from which you start the computations defines the name of data that will be produced in the data subdirectory. I usually run some computations and I redo the computations with modified parameters. So I always put some name with the letters and then 2 digits, like 01, 02, 03. And in some computations, before the results get published, I get up to 30 or 40 in my attempts. So my suggestion is to rename the subdirectory CN graphs to test 01, and then we will start the computations for this test. And there are 2 scripts written in Perl, of course, for running the computations. Run slurm coord, this is starting the coordinator. You know what slurm stands for? This SLURM. This is a new style of batch processing on a computer cluster. Some time ago, it was a PBS. This is a system that supports putting some jobs into a queue, and then when some server is available, this job would run on that server. Now, in Gdańsk, they use Slurm, or Slurm, whatever you call it. That's why the name of the script. But with the argument local, this just runs the computations locally. So it would start the coordinator locally and also 8 workers locally. Let's start this. So we go again to the home directory, and then I copy the commands. The workers are launched 1 per 2 seconds. So that it's because there are also some scripts that look at how much memory each worker takes up, and if it takes up too much memory so that it would cause some trouble to the computer, then this worker is killed, just in case. Okay, so there are 8 jobs running. The top should show there's some problem probably. Okay, something didn't start. Let me see why. This is because I'm using the program USRB time. The time program that shows the amount of time and the amount of resources used by the program that was started. And in this system, they didn't install the program time. I apologize for that. This is my mistake. We should modify the scripts. There are in the test01 subdirectory or the SimGraph subdirectory, depending on whether you change it or not. There are 2 scripts: run 0 PBS and run 1 PBS. This is for the old viewing style. And if you use some text editor at the very end, almost the very end, there is the command USRB time and then the program SimGraph. Just delete this time, and then it should be fine. Also, this one, delete the time, and then this will run. So we delete this data. So I deleted everything from the data subdirectory here, and in the so now I can start these computations again. Well, this always happens with software. Any system that is slightly different from yours, and something will not work. Okay, so launching the workers again. I put the number of 8 workers, but I'm not sure how many threads can be run at each of these computers. For longer computations, it is a good idea to run as many workers, as many threads a system can run. Let's see. Okay, now they are running. So each of them is running at 100% of CPU time. This means that there are at least 8 threads that can be run. Let's see how many threads there are. Okay, 16 threads can be run. So this is some 8-core. At least this computer gets an 8-core processor. So I could run 16 threads at the same time, and all of them would run at the maximum speed. Now, if you look at the contents of the directory data, so there's test01.dat, and this contains the results of the computations. There are also some other subdirectories, like the PNG contains the phase space portraits. Let me just show one of these files. Okay, so this is something that I was shown. And this computation is a little part of that big computation that I was showing here. So this segment, like 5 by 5 segment, taken from here. So what you should obtain is a phase space portrait that looks like this. And now, in order to generate the browser, there is another bunch of commands here. So, okay, we need to enter the test01 directory. I didn't put it here. So test01. You need to add this yourself. And then I copy all this. So the conf.diag script creates continuation diagram based on the results of computations, and the zip data compresses all the data to zip files. Each subdirectory separate. And this another SED command makes a correction to the configuration file of the browser, because the PHP browser actually uses a program for decreasing the size of the image, so that you can. I'll show the functionality of this in a moment. And here's the configuration file, where one needs to hard code the path to this directory. So this command puts home WMI guest 102. This is for my computer. Test01 into this configuration. So now, once we have generated these sets, these files. This is something to do by hand, copying a few files. In the data subdirectory, then test01 that, there are okay, I made a small change in the script, which made it not running. Let me make a correction here. So there's a problem with the commands pset join and pset through. This should be a PNP, another typo. So if you want to edit this file, this is the file conf.diag.pl, and in line 43, there's the command pset join, and then this should be pset to BMP. This is a conversion of a point set to bitmap, and there should be just in quote in parentheses in quotation marks pset join, and then pset to BMP one point stuff. The first one should be with the directory ./pset join, and the second one should be pset to bn. And also, the name of the variable should be set bn. Tonight I am going to put this correction and update the file, so that if you want to try this tomorrow, it should work better than it works today. Okay. And now we start the script. It generates the images, with the data subdirectory, then test01.dat. There are the files test. Browser, which need to be copied to the browser subdirectory. Okay, I think this is correct. And now, so now it is necessary to start the PHP browser. So this is the server. In the last box, the last line is the instructions for starting the PHP server. In case you didn't complete these computations and you didn't generate these files, you can download the files for this picture. And the instructions are in the last line here. Here in the last line. Let me do this here right now to download this. Okay, and starting the PHP server. And now here is the link for the browser. This is running from the local host. You can see the same diagram, and make it a little larger, and you can click these images. If you want to run the picture that was computed, then it was called test 0101, and this is just a tiny section from the original picture. For each box, there is something not working. I didn't copy the data files for displaying the Conley Morse graphs and the phase-space portraits. And there are, let me start another terminal. So these are files in the zip directory, test01 CMG, Conley Morse graphs, and test01 PNG. Due to another typo, I probably need to change the names. They should be copied to the test01 browser zip files. And we need to rename them 01 to 001 because of the mistake. So we make 01 to 001. And then let's see if it works. It works. Yes. And here you can change the maximum size of the image, for example, to 200, and they are rescaled on the fly to the 200 by 200 boxes. We can take some adjacent parameters here in the browser, so we can see how these sets change when you change the parameter values. So yeah, change, and one can click this image to see it full size. Also the graph. Here we've got two sets with trivial Conley indices on the way. And this is because there is something like a period 5 orbit, but its hyperbolicity is not strong enough so that it can be enclosed in an isolating neighborhood at this resolution. I did these computations at much higher resolution in the phase space, and I did find a period 5 orbit there. Nevertheless, here this is an indication that probably something can be found there, but this is not yet mathematically proved. However, whenever you have the Conley index computed, this is strict mathematical result. All the computations are done using interval arithmetic. The system is entered means of C++ code, also using interval arithmetic. So this is computer-assisted proof, like a CAPD, a dynamical thing that we get some results, a comprehensive analysis of dynamical system with with a mathematically rigorous sort of mathematical guarantee that this is correct. Provided the software does what we intend and so on. Okay, so I think this is all for today. Thank you for your attention. I apologize for these typos and mistakes, but this is such a big software that software is a miracle. It's a miracle that it works when it works. Okay, thank you very much.
Any questions for this?
Okay, when you have this Morse that has trivial indices, and you suggest that maybe it's something that is almost can be maybe a salary. I mean, up to some informations. But are you interested in knowing exactly what it is? I mean, it may be trivial, but if you have some continuous information, you get something like a saddle, or it may be some orbits, but which is very slow, like rotating very slow. So
yes. The purpose of this software is to do scanning of all the parameters and classifying all the dynamics that is found there. And this is sort of a first step in the analysis of a dynamical system. The next step would be to see what interesting Morse sets you're getting. And if you are getting interested in those Morse sets with trivial Conley index, then you can do some more specific computations. Now you know which parameter ranges you need to look into. You can do some computations at higher resolution, finer precision. For example, here there's also, in addition to this program for computing the entire image, there's also a program for computing just for one parameter box. So once you are interested in this parameter box, you can change the parameters to do high resolution computation, and then just to do the computation for this one specific parameter box and see what you're getting.
Yeah, I understand that it's possible that maybe you have some of this problem because of the resolution, or maybe you can have maybe two Morse sets that are.
Could be. You never know. And this kind of Morse sets with trivial Conley index always happen whenever you have some bifurcation, because this is rigorous computation and you're computing the outer bounds for the dynamics. So at one side, when there is like this example, in this example, there are some stripes where there is a situation between some bifurcations. There's just one big blob, and here you've got already saddle node, a period 3 orbits, and in between there appears some set. This is this blue one, that has trivial Conley index, and you cannot avoid this. So those regions where you have some sets with trivial index, these are sets within which there might be some bifurcations going on. So you're interested in these sets in terms of detecting qualitative changes in the system, but from the numerical point of view, usually there's nothing you can do about it.
But not every such a set corresponds to a bifurcation, so you never know. Right?
Yes.
Are there any tools to detect bifurcations?
The CAPD group has very sophisticated and advanced software and methods for proving rigorously the existence of periodic orbits, bifurcations, and a lot of very strict things, but they work for some specific systems. You have an equation, you have some parameter values, and then you can do this. This looks like numerical simulations, but this is all done using rigorous computation. And then you can switch to some other tools to do the rigorous proof of bifurcation, for example. Here, the assumptions on the map are very mild. I probably didn't emphasize this too much, but here in the general method, the purpose of the method, there is no even assumption of differentiability, just a continuous map. And in fact, since you represent the map by means of a cubicle map, you only need to know the map up to certain accuracy. So if you want to incorporate some noise or some uncertainty in knowing the map, you can still apply this entire machinery. Some people even try doing this kind of analysis for a map that comes from time series. You start with a time series, then you sort of artificially build a map. From a one-dimensional time series, you can use Packens embedding and build a map on 3D, for example. And then you can plug in this map into this analysis and see what you're getting.
Thank you.
Okay. When you compute one parameter box, how big is difference between 2D and 3D calculation, between 2D and 3D map?
This is, you mean the phase space or the parameter?
The phase space. The phase space. And one parameter box.
This all depends on the actual dynamics. Because if, let me show this on the beginning. Okay. If the dynamics is simple, like it has mainly some fixed points or low-dimensional periodic orbits or low-dimensional invariant sets, then the computations is pretty fast. I did this computation for a 4-dimensional ODE. This was a model of some infectious disease spreading between two cities. And this was feasible. On the other hand, if I do this computation for some chaotic systems, even on 2D, this may create huge Morse sets because the dynamics is transitive. So everything is connected in the graph. And this is a problem. So the problem is not actually the dimension, but the size and the complexity of these isolating neighborhoods that you're obtaining.
Okay, and because I thought similar in some way, and how long takes, for example, I don't know, I can calculate wonderful in one parameter box to be wonderful equation.
Wonderful. Well, it depends on what the resolution you take, but this is a simple system. If a map has is built on, say, 60,000 boxes, this is a matter of a few seconds. If there is like 400,000 boxes for the map to compute in homology, because this is the most time-consuming part to compute the map in homology, then this may take a few minutes. and then it takes like a gigabyte of memory or more. So this is the order of time and magnitude. Here in this, so my approach to using this method is first to start computations at some low resolution. And if I get the diagram that is sort of trivial, like this kind of diagram, if this kind of diagram is sort of trivial, like this, the entire parameter space was just split into two classes. Then I try and see what the dynamics is for these classes, and then increase the resolution. And gradually increasing the resolution, then the length of computations is also increasing until I'm not patient enough. And then I say, let's take another system.
Now, any further questions for Paweł? No, so not. Let's
one another. You say that you cannot keep this like computer assisted proof, yes? Or I missed something.
No, I say that this is computer assisted proof. Yes.
Okay.
So all these results are computationally, are mathematically proved using the computer.
Okay.
So if we assume that the program is correct, the processor is correct, the operating system is correct, the compiler is correct, under all these assumptions, the software is designed in such a way that it provides mathematical proof. For example, this is proof. It is proof that there's continuation defined in some way between these neighborhoods. And also, once you click a box, then you get sets that are proved to be isolated neighborhoods. In particular, the dynamics in this white part is gradient line. This means that every trajectory for the real system, not just for this multi-valued map, must exit this set either in forward time or in backward time. Or this might be a connecting orbit between these sets. It's also possible in the software to compute the outer bounds for the connecting orbits, so that you can see where the dynamics is bounded.
Yes, so let me just add that there are the attempts to actually prove the correctness of programs. There is this Conley initiative, and there are a few others. I don't think they did it for the Horizontal class compiler, which is used in Paweł's case, but we are gradually getting there. So quite likely in a few years, all these intermediate steps will be actually verified. So then it will.
And then there will be another FD bug in the Pentium processor. We're all done.
Any further questions to Paweł?
So, if you have many connections, for example, create connections, when you compute the Morse decomposition, for example, what do you have the Morse set that has all the saddle and the relation between all the saddle, or just Morse set in each saddle?
Let me show the picture with the graph output. Okay, so the entire grid in the entire phase space is represented by means of a directed graph. So each of these circles corresponds to a box, to a grid element in the phase space, and each of these arrows corresponds to the map. If a box is mapped to some other box, then there we put an arrow. So the graph that we work on is the graph that represents the entire phase space and the entire map on the phase space. And then we compute these strongly connected path components. So each strongly connected path component is a collection of vertices that corresponds to an individual Morse set. So we don't get the connections here. Now we get these components, which are the Morse sets. But if we want to get the connections, then we just look at the graph and we take all the possible paths between these Morse sets. And then we get an outer bound for all the possible trajectories between the Morse sets.
I can, okay,
As I suggest you continue with this legal discussion, are you guys both of you sure that there are no further questions at this moment? Anybody else? In this case, let's thank Paweł again. That concludes our workshop. ICM didn't happen in St. Petersburg, it happened in Poznań. And actually, that's a good achievement. Introduction of the computational mathematics. Now there are two groups of people over. Those of you who are living in Poznań, it was great to have you here. Certainly, I think I speak for all the speakers. I hope that you learn new skills, and then we kind of convince you that mathematics is applicable, computable, and useful for industry and in general. I hope you will find it useful for your future careers. So Michał will email you or put the slides, the videos from the lectures on the web page, and then you will get information. And right now, I wish you safe and smooth journey home. And Michał will open the room with the luggages in a second. The group of people who are joining us in band level also follow to grab your luggages, and let's meet 15, 20, let's see, 20 past at the main entrance, which is just over there by the lecture hall. Our bus is leaving half past from somewhere from the parking lot over there. So let's meet over there and then go all together to the bus. Thank you very much for your time. Safe trip, or see you in band level. All the best.